Hello everyone and welcome to another live stream here on 50 Physics, and we are gonna have another review session. So um, I'll get to it. So let me just get into the board, into both the board and the lesson. So right. Right, the student's not here yet. We'll get. Hope she gets in soon. Right, we're using a new board here, of course, because we fresh ran out of the board yesterday. So even though this board is like infinite, uh, I like doing it like this. All right.
Hello.
Hello, Gita. Good day. And how's everything today?
Great. How about you?
Doing great. It's a Friday. Hooray!
Yeah, finally.
All right. So okay. Anything that we're doing today, or
Yeah, it's uploading. I'm sorry.
all right? No worries
Um,
about it.
but I wanted to go over like the content for like resonance and the natural frequency because I don't think I'm very clear on that.
All right.
Um, and also the damping and the graphs
Okay.
for that.
All right. So we'll get to that now once everything's ready. Okay, resonance, damping, and everything. You still there? I think she disconnected. There you go.
I don't know why it's so slow.
Uh, let's just see. Yeah, let's just wait. Maybe, who knows? Maybe it's just the Wi-Fi.
Yeah,
All right.
definitely.
Okay, so still waiting. Just all right. So while we're waiting, let me just go through what I know already. Okay, so let me share my screen. And all right. Okay, still not up. Okay, so let's. I just want to talk about this now since we're still waiting anyway, right? So here
Yeah,
we go.
sorry, I should have done it before.
Nah, no worries about it. I'm just thinking how to approach this. Okay, so I think we went through the basic idea before how damping happens, right?
It's losing energy,
Yeah,
but
that's correct.
I don't
Okay.
understand why we have those categories and
Oh, okay.
like
So what we'll
there's
do?
no formula that differentiates them, so it's just like
Mhm.
some visual.
All right. So first of all, let's start with the idea of no damping. So just simple harmonic oscillation, right? So let's start from there. For simple harmonic motion, um, let's go to no damping for now. Okay. Now, if you have an oscillator, we know that it will oscillate indefinitely back and forth between two positions, like so, right? And this middle position here would be the equilibrium. Okay. Um, in this case, now the idea behind this is because we know that the acceleration is gonna be proportional to the displacement and nothing else, right? So this also means if we multiply this by m, then the force is also proportional to the what's this? The force is proportional to the displacement. Now the main part here is not only is it proportional, but this part in the opposite direction is also important. Okay, reason being, this is the key feature of what's called a restoring force. Now, if you think about it from the name restoring force, it brings everything back to its equilibrium position. So this force will definitely be directed this way and that way, right? Okay, but here's the thing about a restoring force. Another key feature of that restoring force is that it is conservative. Okay, conservative here meanings in terms of the potential and kinetic energy, no energy is lost by this system. Okay, so energy is conserved here. Okay, it's not usually hard to imagine this because gravity, in fact, is a conservative force because that's what happens when something is, well, not really falling but orbiting. Orbiting is SHM in a manner of speaking, right? Okay, so that's a key feature. However, once we have damping, and I see that the images are already uploaded, so let's take a look at that later. Okay, so once we have damping, so if you have your object that's oscillating between um, two extremes, okay, um, in this case, damping happens because there is resistive forces. Okay, so resistive forces exist. And what do these resistive forces do? They are always um, they are not conservative. In other words, well, that's what friction is. Friction, when it's present, it makes the whatever that object is, if it's moving, it loses kinetic energy, right? So resistive forces are not conservative, uh, and at the same time, they are usually not proportional to the displacement. They're proportional to something else, or it could be constant. Okay. Okay. I think you disconnected again. Are you still there, Gita? Or is it me? Let's see. If it's me, then the stream is gonna be bad. Nope, the stream isn't bad. It's not me right now. Uh, all right. So, all right. I think. Are you back yet? All right. Okay. So let's stop for a while. Let's wait for Gita to get back. Yeah, she's the one who's offline. Let's do that later. This one is that idea. Solid. This one. Okay. Ultrasound. Doppler effect. All right, there she goes.
Sorry.
That's fine. Just tell me where you got cut off. Which part?
Um, it's I listened to everything. It's not proportional.
All right. Okay.
Okay, but what causes damping? Like what
So
force? Where does it come
any kind of force that's not conservative will be a source of damping. So air resistance would be one. Friction would be a force that would cause damping. Yeah, those are the most common ones. Okay, so as long as it's not some sort of restoring force, it's gonna be a resistive force, and therefore it's gonna cause damping. Okay, so all right, so that's the examples here. Just write it here. Examples: friction and resistance, air resistance. Okay.
And damping is just one of them. There's also the two other ones. Is it the same cause?
What do you mean two other ones?
Oh, I thought no. There's like 3 types of damping or
Oh
something.
yeah. So all 3 types of damping, they're all because of this. It doesn't matter what kind of damping it is. It's all because of friction or resistance or what other resistive forces there are there. Okay. Now, the kind of damping will now depend on how it oscillates. It's not about friction, the presence of friction or whatever. It's going to be about the amount of resistive forces, which then causes it to oscillate in different manners. Okay, so types of damping, let's do it here. Types of damping. Okay, we have what are we have the critical, subcritical, and supercritical, or overdamping. Okay, so subcritical, we call that underdamping. Okay, we have critical damping, and then we have over damping. Okay, now the easiest way to explain this in terms of a graph is by comparing it to the simple harmonic motion graph. Okay, so what I'll do is I'll copy a simple harmonic graph, SHM graph. Okay, which one will I copy right now? I think which one looks good? All right, this looks good. Okay, study.com, thank you for the image. I'll just need to borrow it here. All right, oops, wrong copy image. Okay, so I'm gonna copy this graph 3 times over for us to compare the graphs. Okay, so this is a position time graph for the oscillation of a body. Okay, so we have that, and we have that, and then we have this guy here. Okay, so in under damping, the idea now is that the resistive force is not big enough. Now I think in DP we don't have to go into the exact detail, but all I'm gonna say here is that the resistive force is small. Resistive force is small. Okay, small compared to the restoring force. Okay, so that makes sense, because if the restoring force is big, then it basically is not affected by the resistive force. It's going to be affected very slowly. So what would you expect to happen to the motion of that wave as time goes on? So this is the amplitude, right? So if we start here at maximum amplitude, we're not going to quite reach maximum amplitude here. And same here. It's going to slowly decrease. But but what's going to happen though is, even though it's decreasing like this, it still oscillates. Something like that. Okay? So what happens here is the object still oscillates with a gradually decreasing amplitude. Okay?
And
Oscillate. Go ahead.
does it come to a stop, or
It will
does it
eventually
go?
come to a stop. Okay?
Okay.
Oscillation. The amplitude slowly decreases. To 0. Okay, so let's just put that here. So that is, again, underdamping. A good example of underdamping would be your normal pendulums that you would see, or when you play with a pendulum, it just keeps swinging, and it doesn't stop until like a few minutes or maybe a few hours, right? Okay, so that's what's happening here. Again, normal oscillations that you would see in real life would fall under underdamped oscillations. Okay, now let's go to overdamped real quick. Okay, that's easier to do with overdamping first rather than critical first, because you see that critical is really the halfway, well, not really halfway, the point right in between overdamped and underdamped. Okay, overdamped, this happens. Did it complete an oscillation? Just from the graph, you see here that in overdamped, the object does not complete a full oscillation.
Why?
Okay. Oscillation. Now I'm going to give you a real oscillation. I'll give you the example here. Let's this time, instead of having that pendulum swinging in air, you're gonna swing that pendulum in water. What happens when the pendulum is swinging in water? It could probably complete a little bit of an oscillation, but sometimes it will just stop right in the middle of its swing. Okay, so that's
Mm.
what overdamping is. So no complete oscillation, and then the object um, stops oscillating, oscillating before reaching one complete swing, or before one complete cycle. Okay,
Mm.
all right.
But these systems, like, how are they categorized? It's not like a normal thing to think about how a
Mm-hmm.
pendulum like swings in the ocean.
Okay.
Like, why do we need to have this categorization?
Here's a common example now that would actually see a swinging door, right? When you have a
Mhm.
swinging door, if it's over damped, that's actually perfect, because when you have a swinging door and you want to, and it closes, if you don't have a damper on it, it's just gonna keep swinging, right? And it's a little bit dangerous if you think about it. But that's why swinging doors have this thing that slows down how the way they close, right? So when they close, they don't actually go complete one full oscillation. They start from the open position and go straight to closed position without slamming into the frame. Okay, so overdamping is in fact useful in certain cases like that. Another common way you would see overdamping would be in shock absorbers in cars. Okay, because they're actually, no, is it overdamped? Yeah, a little bit overdamped, and because of those shock absorbers being a little bit overdamped, so when they go through, when your car goes on top of like a rough road or something, you don't really feel the bumps as much as if you don't have the suspension system or the shock absorbers. Okay, so this is so swinging doors, this is an application, and shock absorbers. Okay, okay, makes sense so far.
Yeah,
All right, so hold on. Am I sharing my screen, or is it black on your end?
I see the screen.
Okay, it's not my camera though, right? It's really the screen.
Yeah.
This is weird. All right, but anyway, so the third part about this is we go into the thing right in the middle between overdamped and underdamped. Critical damping, right? What's gonna happen here for the oscillation of critical damping is, oops, let's do that again. In critical damping, this happens. What's the difference between overdamped and critically damped? Do you see the difference?
It does a bit more of the oscillation.
Mm-hmm. Now, in overdamped, it doesn't complete one oscillation, right? But in critically damped, it does. Okay, or it almost does. So, this is completes one full oscillation or close to it. Okay. Actually, the correct way is it should be actually one full oscillation. That's because normally when we draw these graphs, we start from position like that, like that. But the critically damped one would look something like this. Okay. But since we're starting from this position, the maximum position, so this is still critically damped. Okay, or 3/4 oscillation. Okay, depending on where you start. Now, critically damped oscillations, because of this, they lose enough energy that um they lose the energy just fast enough so that it stops right when it goes back. Okay, so stops right when right at equilibrium position, like as usual. Okay, but in this case, what are examples of critically damped systems? Shock absorbers. Some better designed shock absorbers are actually gonna be here.
What
Okay.
is shock absorber?
Uh, okay. Look under your car and you'll see like a rod with like a piston and a spring in it, in under or right
Mm,
beside each wheel. Okay.
right.
So I think I better just take an image. Shock absorbers.
I think I know what it is.
All right. Okay. So
But this is like, how does the shock absorber absorb just exactly the amount of energy to stop it at the next oscillation?
that's the combination of the springs and the air piston, because shock absorbers are made of two parts: the spring and the air piston. Okay. Now the spring and the air piston, they work together to just really provide you with uh with critical damping, because in certain conditions the spring will provide under damping, but the air piston will provide over damping, or the other way around. The spring could provide under damping, then the air piston could provide under damping. So the combination of both just leads you to have critical damping. Okay. Now, of course, with this, because you now have critical damping, so as again you pass on a rough road, your the wheels could be really really shaky, but it's still relatively smooth inside the car. Okay. All right.
I
Go
have a
ahead.
question though.
All right.
Um, if the graph was a sine graph and it started from 0,
Okay.
if for over damping, would it just not move and it wouldn't have a graph?
Oh, that's a good question. Now, for over damping, it would still kind of move, but it will complete half the oscillation. Okay.
So like half the first curve and then go down.
And then half the first curve, then go down and then go back straight to 0. Okay. So let me see. This is what. Okay, let's just do sine wave. I'm looking for one here. Okay, this works. All right. So if you have a sine wave instead of a cosine wave, well, for under damping, there's no difference. It's gonna be basically the same, right? Okay. But for under damping and sorry, for over damping and critical damping, I'm just gonna draw them here. So for critical damping, it's gonna look more like this. Still complete one oscillation, but stop there. For over damping, it starts here. It still kind of goes here, but still doesn't quite complete one full oscillation like that. So something like that. Okay. Then
Okay.
stop like that. Okay. Anything else?
Like what kind of, do you know what kind of questions you might get with this?
Honestly speaking, this is a new question type that we would be getting, because we've never actually done in the previous years. This was not covered. Okay.
But
So I'm guessing something similar to um yeah, I think it's something similar to the problem you sent over, like this one.
okay.
I'll paste that problem right here so we can go through that. Okay. So I would expect something similar to this. Hold on. Okay, still loading. Let's take a look here. So anyway, so this is the problem from the book where you have the vertical solid cylinder. Okay.
Right.
All right. So um okay, here we go. So in this case, this is just a simple harmonic oscillation problem for the most part, right? So we can, so if we try to answer the simple harmonic oscillation problems here, all we need to do is just apply those ideas here, right? So but I'm going to ask you a question here about damping. Okay.
Okay.
But first, let's take a look at the actual questions. So outline why this cylinder performs simple harmonic oscillation when released.
Because there's a force pushing it down, and then
Mm-hmm.
it's responding.
Okay. So okay. Um, the resultant displace the vertical force on the cylinder is related to the displacement, right? So here's the idea here. First of all, the weight is constant, so I'll do it here. Okay. Okay. The mg is constant, but the f varies depending on how deep the where x is, depending varies with x, right? Now also you can say it like this: if this were the water level, in this case, if it goes down, that's x is positive, right? Or let's say negative because it's down. Okay, but if you're here, the x here is here, and that's gonna be a positive x, right? So you can see that's the f. And then the what's this, it already says here that the resultant, we can actually ignore mg here because f is already resultant, right? The resultant vertical force is already here, and you can see in this case that the force is gonna be here going up this way, and the force is gonna be down here on the second case. So that's the idea. Now let's answer the question: why, outline why this performs simple harmonic motion. So all we have to do is write this down. F is always directed opposite of what's this, of x, right? So this means the acceleration is also proportional to um and let's do it here, and proportional to it, right? So what we can now say here, that a is also proportional to x and oppositely directed. Opposite, okay?
Okay, that makes sense.
Okay. So from here, SHM, thus SHM, right? Okay. So the second part, let's take a look at B real quick. So you're given the mass and the cross-sectional area. The density is also given. All we have to do is put it in here to find F. Okay. So the technique for B here, or the method to do here, is find F, right? Then once you find F, find A. Okay. All right. And once you find A, in this case, I'm just gonna look at the formula. I'm not even gonna put the values yet, right? So because we know that A is gonna be F over M, right? And
Yep.
then we're gonna equate that by changing the F into what it has. That's negative density A G X over M, right? And the thing is, this is your constant. And remember that the acceleration, if we turn it into the equation, that's going to be negative omega squared x. So what do we get here? Omega squared is equal to that whole raw a g over m. Okay? And we find the angular frequency from that. So, put the values in
Um,
afterwards and then get the answer.
oh, and the only reason we connected it to the angular
Yeah,
acceleration is because we know the formula, or
we don't have to connect it to angular acceleration anymore because um, the definition of simple harmonic oscillation again is that a is equal to negative omega squared x if we turn it into an equation. Uh, the reason why we chose omega squared instead of just some value omega is because of the way that calculus works. So we get omega because of it. Oh, omega
Okay.
squared rather. Okay. All right. But either way, since that's omega squared, just substitute, put the values in, find the omega squared. Okay. Now let's do C, kinetic energy. We know how to draw that already. There's a maximum value, there's a minimum value. Kinetic energy decreases, and then potential energy increases farther from what's this, farther from the equilibrium position, right?
Yeah, yeah,
Okay.
we did it before.
See, yeah. So let's go now. I'm gonna ask you a question about damping here, just to complete this discussion. Okay. So in this case, um, um, we can model the equation of this oscillation here, right? But remember as well that there is what. So let's. I'm gonna ask you now. This modeling, this equation, is only a good approximation for a few oscillations. Why?
Mhm. Because there are external forces that act on the
Okay. What are the external
floating
forces that do that? What are the external forces?
viscosity, uh,
Okay.
like friction.
The friction, right? The friction between the water and the cylinder, right?
Yeah.
Okay. What else can be possible here?
Mm, the drag
The
force.
drag. Okay. Yeah, could be the drag. So any kind of resistive force would do that. So now, if it's now, so basically, I think those are gonna be the questions here. Just say why it would not be, what the damping forces are. Okay. Now, another possibility here is for you to determine whether it's underdamped, overdamped, or critically damped, right? In those cases, there is no other way around it. All you really have to look at is how many times it oscillates. If it oscillates more than once, underdamped. If it oscillates exactly once, critically damped. If it doesn't oscillate one full swing, overdamped. That's all you have to do here. Okay.
And how do I know how many oscillations it has?
You just basically count how many waveforms it makes. Now, basically, if it's a very simple thing like a pendulum or a spring on a mass, right? All you have to do is count whether it goes back and forth, how many times, right? So once it goes back and forth several times, it's already considered under damped. If it goes back and forth only once, critical. If it doesn't, again, so okay, I think I'll go to normal camera real quick just to show you what I mean. Where?
Because in this case, I don't have a graph, so can I
Mm-hmm.
find how many oscillations it does? So,
Yeah. Okay. So if we go back to the graph. Okay, let's just go back there then. Okay, before I change. So let's go back to that graph. So in this graph, these graphs, right? So you see here in under damping, how
yeah,
many oscillations do we see in this graph on the red line?
like two
There's
about.
that's around two oscillations already, right? So because we have more than one oscillation, under damped. Okay. Now, if we go here to the critical damping, you see it's still again, if we extend this further into the negative time territory, we kind of get like a full oscillation still. It doesn't quite go to the amplitude that it needs to be at, but it still completes one full oscillation, right?
Mhm.
Okay, critical damp looks like that. Over damp, you see it doesn't even reach like halfway through the thing. So again, when it comes to the graph, all you have to count is how many oscillations it makes. It doesn't even have to be full amplitude oscillations, just oscillations. Okay.
Uh,
So yeah, this is still like one oscillation, even though it didn't reach to like 3 centimeters here compared to the what's this compared to the no damping situation.
and do you think they will be given both the curves in this case? So like the sine curve, the usual, and the critically damped or the over
There
damped?
is, I have no idea if it's gonna come up or not. I'm
Mm-hmm.
going to guess that it may, because this is one way for us to visually represent damping. This is the
Okay.
only visual way that I can see that damping is done. Okay. Good evening. Oh, somebody's on the stream. Good evening. I hope you're still there. All right. So, and hope you're learning. All right. So carrying on, and anything else you'd like to ask about this?
Um, it's clear. It's
All
clear
right.
for now.
Um. Okay. So again, in terms of the exam, I don't know what exactly will come up because I'm not the one making it. But um,
Yeah.
guessing from what they actually do, what damping does, this is the best way that I can think it will come up. Okay.
Okay.
All right.
Um,
Go ahead.
actually, one question.
Go ahead.
If we didn't have a visual representation and they gave us a task,
Mm-hmm.
is there a way that we can find how many oscillations it does before it comes to rest
Um.
without simultaneous motion?
I okay. The best one I can think of really is you can compare the magnitudes of the forces. Okay.
Mm.
If the if the restoring force is much bigger, I think I'll say it like this here. So I think I'll add it here then. Okay. So in this case, the restoring force is gonna be much larger than the resistive force. Okay. So restore. Okay. In overdamped, it's the other way around. The resistive force is larger than the what's this? The restoring force. Okay. So basically for critical, this is not 100% true, but we can at least say that the resistive force here in critical damp, resist, is approximately equal to the restoring force. Okay.
Okay.
So I think that's the second best thing we can do at this point without knowing what the exam has.
Okay.
Okay. Which makes sense. Think about it, right? Because if in the first case, if the resistive force is small, it's basically nothing. It's just gonna keep oscillating. Okay.
Yeah.
All right. All right. Now you've sent over two more questions. Um. Okay. Let's go through these questions now before we run out of time. Um. All right. So hold on. The first question I'm going through would be the one with where you have the two samples of the same materials. Um, they're allowed to reach thermal equilibrium without exchanging thermal energy, and the graph shows the temperature as of each sample as they vary with time. The sample of the mass 2 is 600. Ah, okay. This makes it easy. Okay. This looks complicated, right?
Yeah.
Actually, it's not. Because here's the thing. The idea here is that the hotter object transfers all its thermal energy to the colder object. So this is gonna be energy 1, right? Or change in energy 1, right? And this is gonna be change in energy 2. And because of conservation of energy, they should be equal. Okay? And since the next clue here is that they're the same sample of the same material. So all properties are the same. In this case, we're looking at the specific heat capacity. Specific heat capacity. This is going to be C. In this case, they have equal values. Okay. So this already tells us something. The E1, this will be equal to M1 C delta T. 1. Okay. And this is going to be the same here. It's going to be M2. That's going to be there. M2 C delta T2. Right?
Mm-hmm.
Um, what Okay, so and since they're equal, I'm just gonna put that in a box so we don't confuse that as a bar. Since the two energies are equal, we're gonna equate these two right away. So M1 C delta T1 should be equal to M2 C delta T2, right? C cancels out immediately. We don't need to know what it is because they're equal. We know the mass of one of the objects, sample 2. That's 600 grams. So 600 here, right? The delta T on sample 2, let's take a look here. It's from 10 to 30. So the change here is 20 degrees. Okay? So 30 degrees minus 10 degrees C. Okay? The same thing here. We don't know M1, but our delta T for M1, we can see it from the graph. We go from 30 to 40 because we start off at 40, right? Actually, I forgot. This should be here. This should be negative here. Okay, so this is gonna be negative. So there's a negative here. This is gonna be 30 minus 40. Okay, degree C, degree C. So this is gonna give us negative 10 and negative. So that's gonna be M1, 10 M1 now, right? It's gonna be 600 grams times, this is gonna be 20 degrees C. Okay, so the degree Celsius cancels out. We're left with M1 is equal to 600 times 20 over 10. That gives us, did I do the calculation right? Hold on. Yeah, correct. So that's going to give us a mass of 1,200 grams. Okay.
And why is M1 negative?
Um, because the idea now, if we go back here to the graph, the energy is lost here, right? So this is M1 loses energy, right? And here M2 gains energy. So
Oh,
because it loses energy, we need to have a negative sign here, and therefore we need to have a negative sign here. This gains, so this must be positive. So this is also positive. Okay.
and it wouldn't be accounted for if we made the temperatures negative.
Uh, Actually, it would be accounted for. Because honestly speaking, this is the more correct, the more mathematically correct way to do it. You put the negative sign because of the loss and the gain, right? Positive for gain,
Mhm.
negative for loss. But the change in temperature is also going to be negative anyway because you start on the gain, you go from 10 to 30. So you increase temperature, right? But on the
Yeah.
losing energy, your temperature changes negative because you go colder from negative 4 from 40 to 30, right?
Yeah.
So
Okay.
those changes basically cancel out in the equation, right? And therefore the answer here, since we have choices, the answer here D. Okay.
Okay.
All right. So that's the long way. The short way is realizing that the energy change is smaller for sample 1 and therefore it must be more massive. Okay. All right. That question's done. Anything else?
That's okay. I understand.
All right. Let's go to this question you sent over about damping. This one is a little bit different. Um, okay. This looks like a university level question. But,
I'm pretty sure it's from the book.
oh, if it's in the book, then okay. Hold on. This question is about the damping, heavy damping, light
It's
damping, driver and moving phase. Okay, this one's a bit tricky now because we are now including not only damping, but we now have an oscillator, right? We now have a
yeah.
driving frequency, a driver. Okay. Let's take a look here. What does this mean? In certain situations, you can have resonance. So resonance is gonna be important in this particular idea. So remember, resonance occurs. Resonance occurs when the frequency of the driver is equal to the frequency of the oscillator. Okay. Okay, so again, when the end, there's a condition here, and the two are in phase. If they're out of phase, you're gonna get a lot of damping, at least at the beginning. Okay. All right. So what? Let's take a look here at this diagram now. Light damping, driver leads by half a period. Heavy damping is that. Okay. What's this? Phase lag and radiance. Okay. This is basically this phase lag. Basically, this is the phase difference. Okay. In other words, if they're moving together, the phase difference is zero, right? So this is exactly what we were saying earlier. If the phase difference, if the two are in phase and the two frequencies are the same, then there's no damping. Okay.
But why does it have to be labeled there if we know that there is no phase difference?
Because later on, what will happen with this graph basically is as you so this is the driver frequency on the what's this on the x-axis, right? So basically, this is just telling us that at the phase. Okay, hold on. Phase relationship between driver as the frequency changes. Okay, so here, when the frequency here is when the driver frequency here is f0, and then what's this? The phase difference is like a 0 as well. So basically, what happens here is it's kind of hard to explain real quick from what I'm thinking. Let me simplify it first. Do it in my head first. Okay. Heavy damping is this. Okay, so this is the idea now. The best way I can really think about this that would make sense is this, okay? Now, if you had no damping, I'm gonna put the no damping phase diagram. Okay? No damping. Okay? So what else do I need? The driver frequency is equal to f0 and okay. So no damping basically looks like this. Okay, what does it mean? So whenever you have a driver, whenever you have something that's pushing something to oscillate, right? Um, if your frequency of pushing, so to speak, matches the frequency of the thing that's oscillating, then what's gonna happen is that amplitude just keeps increasing and increasing, and at the same time the phase difference stays zero. So basically, that's what it means here. Okay, but if you have light damping, you're gonna have to be you're because the oscillator is not really moving like it would without damping, but it's still moving close to it, right? So this is what this part means. When the damping is light, you don't actually need to be um right, the driving frequency doesn't actually need to be exactly near exactly here. Okay, it can be a little bit behind. In other words, if the frequency of oscillation is 1 hertz and it's light damping, the driver can have an oscillation of like a frequency of 1.1 hertz. It's close enough. Or 1.2 hertz. Okay, because the object is actually slowing down, and therefore there's a bit of lag, so that the oscillator needs that lag a little bit, or the driver needs that lag a little bit, so that it can push that other object at the right time. Does that make sense? Okay.
Yeah, so the bigger the difference is, the bigger the damping.
Yeah, and the bigger the difference, the bigger the damping. Correct. And this is one way for you to check, to experimentally check whether it's critical or heavy damping or light damping.
Okay.
Okay.
And this example, it's when we have an already oscillating object and then we just put a driver
Uh-huh.
and another frequency.
Uh-huh. Now, what else does this mean? Now here, in this region here, they are moving together. The driver and the driven are moving together. Okay. In this particular region, so I'm going to really highlight that. In this particular region, it says here the driver leads by a quarter of a period. In other words, um, let's use the frequency of 4 hertz to make it easier. Okay. So if the driver leads by a quarter of a period, then that means it's also oscillating at 4 hertz, but it's maximizing by 4 hertz. Sorry, period. Let's use period, not frequency. So the period is 4 seconds. Let's make it easier like that. If the period is 4 seconds, then the driven object, it oscillates once every 4 seconds, and the driver oscillates once every 4 seconds. But the way they're not moving together like right in phase. So one is moving a little bit behind compared to the other. Okay. So hand wise, I think I'll show my hands here to show you okay, show you something like this. Hold on. Hey, I'm getting engagement. Nice. Thank you for those questions. Yeah. All right. Going back here. So going back to my hand, zero. If they're in phase, they're moving like this, right? In the driver leading by a quarter of a period bit. Hold on. Let me go to main camera. If we're going, if the driver leads by a quarter of a period, it's more like this. So this is oscillating like so, but this is not oscillating like this anymore. This is more like so, little bit laggy. Okay. The other one, the driver leads by half a period. The driver leads by half a period. It's now the driver that's going first, so to speak. So something like that. So this is the first part. The one near the zero, the one near the origin is going to be something like this. The one on the lower half on the right is going to be something like this. And the one on the upper half is going to be the other way. It's the driver going first. Like that. Okay. Hard to visualize, but I hope that helps.
Yeah, it does.
All right. Okay, so okay, so that one's done. What's this other one here? I think we can finish these two here. Okay. These two things you just sent over, the last two things you sent over, I think this is Doppler effect. The other one, the one with the equation, is definitely the Doppler effect. Okay. Let's go to this one first. Ultrasound measurement of blood flow. Yeah, this is definitely Doppler effect. The second one, I'll just copy this as well. This is actually in the data booklet, this other thing.
Oh, the formula.
Yeah, that is the formula in the Doppler effect, right?
I couldn't find.
Okay. Why is that the case? There. Let's just put it together. Now, the reason why why the Doppler effect is going to be useful here is because okay, there we go. Rotate that and put it here. Okay. So the idea now is when the sound is going into the bloodstream, some of it will be reflected back, right? Like that. But remember that the blood is moving this way. So we really need to take into account that angle theta in calculations, right? So if you think about it this way, I'm going to just where would theta be? Theta would also be here, right? So if we simplify that, you remember the thing where we simplified by changing our angle of view. So this is going to be the same idea here. If this is your transmitter, right? The sound goes in like that and gets reflected back. But the blood is moving this way. So there's an angle theta, right? If the blood is moving this way at the velocity v, then we know that the blood has a velocity going this way, has a component of the velocity vx this going that way, and that is very simply v cosine theta, right?
Oh, yeah.
Right. And what matters in the Doppler effect, let's put the vy just for argument's sake. I'm not gonna say the v sine theta anymore, but we know that the Doppler effect, the vy doesn't really matter much. It's the vx that matters, right? So because of that, we can actually estimate the Doppler effect using only vx. So we use this in Doppler effect formula. Use this in, well, bad color. Use this in Doppler effect formula.
And
Okay.
why doesn't Vy don't like doesn't matter?
Because, well, it kinda does, especially once you get like going really really fast. But in this case, remember, you're in a blood vessel. That vy is gonna be tiny because of blood vessel, right? In blood vessel. Okay. And because it's tiny, we can just ignore that. And because we can ignore that, we can basically use v cosine theta here, and that's why our formula here has that cosine theta here. Okay. Now in this case, what is the v that we should use? Remember, in the Doppler effect formula, this should actually be properly called u, because v is the speed of sound, right?
Right.
Okay. So that's why in our formula we have the u cosine theta in here. All right. Now, y2, you have to do it twice. One for going away, one for being reflected back. Okay. Now, the reason why it's approximate like that is because the last thing I'm gonna say is I'll go back to the what's this? Data booklet. Let's go to the data booklet here. Okay. Give me a moment while I pull up the formula. Again, this is one of those formulas I haven't memorized yet. Where is the actual Doppler effect formula? Okay, here. The actual Doppler effect formulas for the moving source and the moving observer are given, and you're also given this approximation in the SL section. This equation is in the HL section, right? So the idea now is we're gonna separate the two movements. The first movement is, this is the source sending the ultrasound, and then this is the blood cell, right? And that blood cell is going like that with a speed u, right? U, and then with the speed v here, right? So in this case, we can consider this to be the moving. Is this the moving observer or the moving source? This is the moving observer, right? So we're gonna have to use this formula here. Now, when the light, sorry, not the light, but when the ultrasound is reflected, it's gonna be like that. But now, because it's reflected, it's now the source, right? So this is still moving at the sound at the velocity u. This is now going at v, but this time, because the sound is reflected, this is now a moving source. So in other words, you're gonna have to use both of these formulas. So there's a change in the frequency because of the moving source thing, and that's gonna be here. And then you're gonna have another change in the frequency because of this thing, right? So if you add the two changes, you're gonna have to add the two changes. So if you add the two changes, that's basically let's label that f1 f2 for now, right? So f1 prime plus f2 prime, that should be equal to, in this case, sorry, we do the first one. Okay, sorry, my mistake, not like that. There's a better way. Okay, but the better way here is we're gonna use let's do 1 here and 2 first, right? So we know the frequency and we know f1. We can find f1. Then we use this to be f1 prime because that's the new frequency from the moving source. But if you put that in there, what are we gonna get? F2 prime, that's going to be f um f1 f times u plus v plus or minus u0 over v, and then v over v plus or minus us, right? But here's the thing, all our u's and v's are the same, so that cancels out, right? Right? And but these don't quite cancel out because they add up, because one of them is minus, the other one is a plus, so these two don't quite cancel out. So that's gonna be well, whatever it's gonna be, it's not gonna be exactly f. But here's the thing, if you calculate that tediously, that's gonna be approximately equal to 2f, essentially. Okay.
Okay.
All right. So and then if we do the rest of the calculation, we'll get the actual formula there. Okay. So again, I don't want to go into the whole detail, it's a bit long to do. Okay.
Okay. I understand
All
though.
right.
It's really interesting.
Mm-hmm. All right. So okay, somebody's really in the stream now. This is nice. All right. So
Ooh.
all right.
Yeah.
Sorry, no super chat just yet. I'm not qualified for super chat just yet. All right. But did I hope I answered all the questions earlier, yeah? For that in the stream. All right. Gita, do you have any questions before we end today?
I don't have any questions. I'll
All
just
right.
go over this and yeah.
Okay. All
Thank
right.
you
So
very
I'll
much.
send over this link to this board and hope you can use it for studies. Okay. All right. You have a good
Okay.
day and have a good weekend. I'll see you again tomorrow. Goodbye for now then.
Okay. Bye bye.
All right.
Thank you very much.
Bye bye. All right. So that's the end of that lesson there. And yeah, thank you. We have some sort of engagement. Um. Uh. Okay. So who else is here? So yeah, sorry, no super chat just yet. But yeah, was I able to answer your last two questions though? Let's go back to the main. Don't call me professor. I'm not one just yet. But yeah, you're welcome either way. All right. Okay. So I believe I answered the question. But yeah, later on, if we will be coming back tomorrow, so to help you with that, yeah, I'm gonna be here at. We're gonna start at this time. We're gonna start at this time tomorrow. Okay. So if you'd like to go back here tomorrow to join us and just be studying for physics. Remember, I think most of you are here because the exams are coming up on Tuesday. Well, Tuesday here where I am, right? All right, so good. That's okay. That's great. Thank you for that. All right, so we can end today's stream, but before we do, um, yeah, don't forget to like, share, subscribe. We are now here on YouTube, Facebook, and Twitch when we go live, and then we do get announcements on Instagram and well, not quite TikTok yet. I'm still setting it up, but yeah, we do have a TikTok as well. So follow us there when you can. And we'll end the stream here. But before we do, I'd like to wish you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.